So we have 30 members, so 30 subjects. So this is a within subject design, and we can use a matched pair comparison t-test. Problem being that we don't have before after. But is it necessary? We already know the answer to that. But let's look at it from a research hypothesis perspective. If someone did this research, they would have hypothesized that the after weight of a person is less than before. Agreed? Yes? If you start with a member who is 170 pounds, and if they went through the program, we expect them to reduce to 162 pounds, for instance. Correct? So, by looking at the data right here, a good amount of numbers are positive. Correct? So, after minus before will work. But if we want to go through a case where we should have no confusion whatsoever, right? I'm making a huge assumption that the difference is after minus before. But if I don't want any confusion and I just want to see the conclusion, what test is better? I'll give you three options: right-tailed, left-tailed, two-tailed.
Can you ask the question again?
So in this case, I suggested if I'm a researcher and if I have to make a hypothesis, I would have defined it as before minus after. Yes? Because if you start at 170 pounds, after is 162 pounds, then there is a decrease. I'll have £8 difference. But that is an assumption. Agreed? Now, if it is the other way around, this negative 10 would mean a lot to me. If I want to avoid confusion entirely, what test will I use, or should I use? Right-tailed, left-tailed, or two-tailed?
Never answered.
I like the left-tailed based on tailed due to your hypothesis, hypothesizing that they lose weight.
So Jonathan says left-tailed because I'm hypothesizing that they lose weight. Do we agree with Jonathan?
No.
Why not, Phoebe?
Well, we said two-tailed because then you can like see your, I guess, loser.
So you're going to say two-tailed?
Yeah.
Very good. That is the
Oh,
correct
dude.
answer. So since I don't know how I define the difference, I would rather go for a two-tailed test asking the question, there is no difference at all. This exercise program is not worth it. And the case where I would go for there are differences. So a proper hypothesis in this case would be to use So we're going to use two-tailed test because if it fell on the left tail, we can conclude there is a difference. Right tail, there is a difference. Otherwise, no difference at all. Last time, Cleo asked me a question. Well, why bother defining x and y when you can simply put in the difference? That's exactly what I'm about to do. If we have x observations before, y after, then when you use t-test, it will do x minus y. But if you don't want to do that, you can simply put the difference, which is exercise loss. That is the amount of loss, the difference is directly. And we have to specify a null value. The null is no difference at all. So mu is 0. We have decided to use a two-tailed test because we don't know how we define the difference. The rest of the parameters in t-test are fixed values, default values. The confidence level is 0.95, which would mean alpha is 0.05. And that is the results that I'm getting. So just by looking at it, what is the test statistic? 2.7654. If you round it, 2.77. P-value 0.009786. It's concluding that the true mean is not equal to 0. The average is 3.2333. The confidence interval 0.84, and we have 5.624 minimum and maximum. So based on the test, we have concluded that there is a difference because of the exercise program. So the null is the average mu underscore z equals, or d equals 0, which means no difference. Alternative, there is a difference. So our conclusion is to reject the null, in which case we simply mean that the exercise program has an effect on grade. Here is a question in terms of interpretation. What is the minimum value at which you can reject the null based on the result that you saw? Come again.
Anything bigger than 0, you can reject the null.
So if anything bigger than 0, you can reject the null. So what is the minimum probability at which you can reject the null? To avoid a false positive. Let's add that too.
Would it be what's listed as the p-value there?
Would it?
Yeah.
Okay. So we know that alpha is the probability of type 1 error under the null. And the minimum value at which I can reject the null to avoid a false positive was 0.05. The data is telling me, well, forget about that. Based on the data, if I condition on the data, so I'm going to put that vertical dash, the value that I get is 0.00, I believe it's 9278, no, 9786. So the rejection region corresponding to 0.05 is my limit. But it says, well, you can actually reject it if it hits below 0.009786. What this means is if I've repeated the experiment over and over again, the smallest p-value that you can expect is 0. Or smallest value of alpha, which is the p-value. Is 0.009786 based on the data. What I set is at 0.05. So since this is the frequentist approach, if you repeated this experiment, the value will fall, or the probability will fall between those two endpoints. That simply means no matter how many times you try, 95% of the time, you will be rejecting a null if this data or if this experiment is repeated. Another easier way of interpreting, well, alpha is the probability of type 1 error under the null, a false positive. You rejected the null and concluded that there is a difference. The exercise program has an effect. Well, what are the chances that you are wrong in concluding the exercise program has an effect? The chances are 0.9786%. That is the probability of an error. So knowing that probability, should you comfortably reject the null? Yes. If the chances of an error is very, very close to 0 based on the data, and I'm telling you, no matter how many times you repeat, 95% of the time, I'm going to get an alpha or estimate of alpha between 0.05 and 0.009786. So I'm guaranteed to go below my 5% threshold. So I can comfortably reject the null and conclude that there is a difference. Good. That's it. Phoebe, do we follow?
Yeah.
Others, actually. Any questions before we go further?
Let's do another one.
Now, here is another question. So we know that there is a difference. Now the question is, did the program work?
Wait, we don't know.
Very good. We don't know. So you look at this average, I get 3.2333. So that is the average difference. Well, let's say I define the difference as after minus before, and I get an average of 3.233. What would that mean? We already know it is statistically significant. There is a difference. My question is it an effective exercise program if after minus before is 3.233? Let's say you have 160 as after, before 163.23, or sorry, before minus after. Oh no, after minus before. Then 3.23 difference, that means you gained weight by 3 pounds. Well, if I did it as before minus after, and you had 163.23 here for before, and after is 160, you have a difference of 2.33 on average. Here, the exercise program is worth it, correct? So as if now the test can only tell us if we found an effect or not, but we cannot come to a decisive conclusion as to whether it resulted in an increased weight, which would mean it is an effective, useless exercise program. If it resulted in a decrease in weight, then that is an effective, useful exercise program. Good, Omar?
The way the data was stored is that it had that as weight loss. So I feel like it implies that it was that a positive number would imply weight loss and a negative number would imply weight gain.
It is a good assumption to have, since they have called it weight loss. They would have done it as before minus after. If I have to choose between these two, I would go for before minus after, but I don't like making assumptions. I would rather ask the person as to how you defined the difference. If you ask me, I'm about 99% sure that this is before minus after, but I don't want to make that assumption without more information. Good? So, I would say perhaps, provided the observations for the variable loss based on A equals before minus after. Again, I'm 99% certain that's what they did. But I just don't want to make that assumption. Are we clear?
Yeah.
Yes. So that's how you do a t-test for dependent means. This is called a matched pair t-test, a t-test for correlated means, a matched comparison t-test, different names, same thing, happens in two different experimental settings. First, repeated measures design. Second, within subjects design. Are we clear? Okay.